Hey there, it's Shannon Math Chick Myers, and today we'll be looking at section 15.4 from the calculus text by Larson and Edwards. And I wrote the guided notebook for to accompany this, and we're looking at Green's theorem. So pretty much just you got to understand this is just an overview. When you get to advanced calculus, you'll be looking at all this stuff in chapter 15 with a lot more depth and proving all these theorems. But I want you just to be able to utilize the information and the techniques. So, are you ready? Why don't we warm it up? Go ahead and pause the movie and warm it on up. I know you can do it. On your mark, get set, go! Okay, let's see how you did. This is, from a little while back, vector valued functions. So let's go ahead and represent the plane curve 2x minus 3y plus 5 equal to 0 by a vector valued function. So here, one way we can do this is by isolating y. So what would we have? We would have negative 3y is equal to negative 2x minus 5, and then dividing by negative 3, we would have a 2/3 x plus 5/3. The easiest way to do it is probably just to let x equal to t. And if you have x equal to t, then y will equal to 2/3 times t plus 5/3. And then our vector valued function will be r at t is equal to t times I plus 1/3 times 2t plus 5 times j, or something like that. Groovy? All right, so now let's determine, number 2, we want to determine whether the vector field f is conservative. If it is, find a potential function for the vector field. So we've got this in space. This is a vector field in space. So, it should be relatively easy in the sense that the derivatives for, the first partials with respect to p, which would be the coefficient for k, will be 0. So that will make it a little easier. Let's go ahead and, identify what we've got going on over here. M is the coefficient to the I. And so m is equal to x over x squared plus y squared. So the partials we need for m are the first partial with respect to y, which will be, 2xy, that'll be a negative. And then we'll have x squared plus y squared, the quantity squared. And then we will have, we need the first partial of m with respect to z, which of course is 0. There are no z's in there. N is equal to the coefficient to the j vector. So that is y over x squared plus y squared. So the partials we need for n, we need the first partial of n with respect to x, which will be negative 2xy over x squared plus y squared squared, using our chain rule again. And we need the first partial of n with respect to z, which will be 0. There are no z's in n. And p is just equal to 1. So dp dx is equal to 0, and we also need dp dy, and that's going to be 0. Groovy? All right, let me move these over. a little bit. Okay. So now let's see what needs to be equal. Remember that the first partial of p with respect to y has to equal to the first partial of n with respect to z. So are they equal? Let us see. So where was our dp dy is 0, and then dn dz is 0. So those match up. So of course we're checking to see if this vector field f is conservative. And what else needs to match? We need to have dp, the first partial of p with respect to x, has to match the first partial of m with respect to z. So dp dx is 0, and the first partial with respect to first partial of p with respect to x is 0, and the first partial of m with respect to z is 0. And then finally, the last two are equivalent. We have our first partial of m with respect to y is equal to the first partial of n with respect to x. So we're good to go because of these equivalencies. We can say that f is conservative. All right, well, since f is conservative, what do we need to do? Beautiful, we need to find a potential function for f. So in order to do that, what we need to do is we need to integrate m with respect to x. So that will equal to the integral of x times x squared plus y squared to the negative 1 dx. In order to integrate this, what do we need? G is x squared plus y squared. So the first partial of that with respect to x is 2x. So we need a 2x dx. So if I multiply by 2 and then on the inside and by 1/2 on the outside, I shall be able to integrate. So I will get natural log, or 1/2, natural log absolute x squared plus y squared, but that will be positive, so I will not need absolute value. And that will be plus some g of y and z. The integral of n with respect to y is going to be the integral of, so n was y times x squared plus y squared to the negative 1s, but this is with respect to y. So again, very similarly, this time we'd need a 2y in order to integrate, so we'll multiply by 1/2 on the outside, and we'll get 1/2 natural log x quantity x squared plus y squared, and that's going to be plus some h of x and z. Groovy? All right, so now we have the integral of p with respect to y. Well, that's going to be the integral of 1, or sorry, this is with respect to z, bad teacher. And so that would be the integral of 1 with respect to z, which would just be z plus some function, call it k, of x and y. Groovy? All right, so anyway, this is what we have going on. Notice that we have 1/2 natural log x squared plus y squared in here, that first line, and in the second line. And so that is our function of both x and y. That will be our k of x and y. Groovy? And then our z, or function that has z in it, is just z, right? So we will have g of y and z is equal to h of x and z, which will equal to z, and then we'll have some constant k. All right? So our potential function will be f at x, y, and z is equal to, and let's pretty this up a little, 1/2 times natural log at x squared plus y squared is equivalent to natural log at the square root of x squared plus y squared. And then that was our k of x and y plus z plus some constant k. Groovy? All right, so we found our potential function. And we're good to go. Hopefully you're all warmed up. And we're going to now take a look at simple curves. So a curve C given by r at t equals x at t times I plus y at t times j, where t is between a and b inclusive, is simple if it does not cross itself or intersect itself. So that is that r at c is not equal to r at d for all c and d in the open interval from a to b. So a plane region R is simply connected if its boundary consists of one simple closed curve. So if you have something like, I don't know, if you just have something like this, and let's say it's oriented like so. I know I get a little ADD about my arrows, sorry. And call this region 1, okay? And we'll be talking about these regions with Green's theorem. So the simple curve, okay, is the outline, right? So this is, so this region R1 is simply connected. Cool. But if you have something like, I don't know, like something like this, right? Where, let's say it goes like this. Do you see how it intersects itself? And so this is not going to be a region which is simply connected, right? So this here, region 2, right? I'll just put it in both spots, region 2, right? Is not simply connected. And that's because of this point right here, okay? So now there's another potential thing that could happen. You could have some region that looks like this. Let's say you've got something like, sort of like, what we had in R1. But then you've got, so that one, if it was just that, would indeed be simply connected. But then let's say you also have something inside there. So now it's no longer simply connected. So here, this region 3 is not, R3 is not simply connected. Cool, cool? All right, awesome. So now, what Green's theorem tells us is this. If R is a simply, or let R be a simply connected region with a piecewise smooth boundary C oriented counterclockwise. So that is, C is traversed once so that the region R always lies to the left of C. So if M and N have continuous partial derivatives in an open region containing R, then it turns out that the integral over our curve, our smooth boundary C, M dx plus N dy, remember that weird thing about not having the parentheses with these line integrals, ends up being the integral over the region R of the first partial of N with respect to X minus the first partial of M with respect to Y dA. Okay, so first example, verify Green's theorem by evaluating both integrals. All right, so the integral along the curve y squared dx plus x squared dy equal to the integral on the region of the first partial. Sorry, the notation's bad right here. This should be the first partial of n with respect to x minus the first partial of m with respect to y, with respect to the area region for the given path. So the triangle with vertices 0, 0, 4, 0, and 4, 4. Right? So let's check it out. You've got this triangle. And it's got vertices where? At 0, 0. Okay, 4, 0, and 4, 4, like this. So if it's starting here, it's 0, 0, because remember we want it to go counterclockwise to use Green's theorem so that the region's always to the left. So it's going to go like this. Good so far? All right, so what we need to do is we need to find our, the old way, right? The old way would be we need to find our piecewise vector valued function and then do, the integral that we end up needing to do. So we'll go over that first. That'll be kind of a review of what we did. I think it was the last lesson or the lesson before that. And then we'll go from there. So R at t will be equal to, so from t going between 0 and 4, it's the horizontal line y equals 0, right? So you're always going to have an output of 0 for your j vector, but your I vector will vary along t. And so you're going to get t times I for 0 less than or equal to t less than or equal to 4. So that's this right here, this piece. Groovy? So for our second piece, what will happen is that is the vertical line, x is equal to 4. So you're always going to have 4i, right? Now, t is going to vary between, it has to start at 4, right? So y does vary from 0 to 4, But we have to come up with an expression so that t is going to start at 4. So I believe if we say t minus 4 times j, and t varies between 4 and 8, I think we're going to get what we need. So let me move this one over. Okay, so then you just test it out. So if t is 4, I would have 0 times j, so I'd be right at 4i plus 0 times j, which is perfect. If t is 8, I'd be at 4i plus 8 minus 4 is 4j, and that's perfect, right? So we're good to go. Whoa, on this one. So that's this piece. And then lastly, we're going to have t now, y is going to go down by 4, and x is going to go, to the left by 4. So basically, t is going to range now, I think, between 8. We know it's got to start at 8. So why don't we call it t, let's see, not for this one, we need to get to be a point at 0, 0 on your very end, and the point has to be at 4, 4 at the very beginning. So when I'm looking at 8, it would need to be, if I had 12 minus t times I, and we start at 8, that would be 4i, and that's perfect, right? And then I believe we're also going to have 12 minus t times j. And that starts us off at the vector 4, 4. And if t goes on to 12, that leaves us at the vector 0, 0. So we're good to go. Groovy? Okay. So for this one, let's see what will happen. We've got our r at t, and it's these 3 pieces. And so what we needed to find was, at the end of the day, we need to find all of these pieces, right? So our first one is going to be so for our first piece, we have x at t equal to t, and so dx will equal to dt. Y at t, there is no y at t because it was 0, right? It was that line y is 0, and so dy will be equal to d0, no, 0. On the interval from 4 to 8 for t, we've got x at t is 4. Sorry about the dogs. Dx will be 0. Y at t was t minus 4. And so dy is equal to dt. And then that last one we worked on, that last curve, is going to be x at t is equal to 12 minus t, so dx is equal to dt. Y at t is also equal to 12 minus t, and actually dx will be negative dt, right? And so dy is going to be equal to negative dt as well. Groovy? All right, so then what do we do after that stuff? Well, we have to now go up and combine all these integrals, right? So we would end up having the integral along the curve of y squared dx plus x squared dy. So our first integral is going to go from 0 to 4, right? And y at t was 0, so we'd have 0 squared dx, which is dt, plus, and then x at t was t, so then we'd have t squared, and then dy was 0, so that whole thing will zero out. Our second one in this blue would go from 4 to 8, right? And y at t is t minus 4. And dx is 0. So this would have been squared here. And then plus x squared, which is 4, or x at t, that'd be 4 squared. And dy is going to be equal to dt. So then we would have the last one. We'll end up with the integral from 8 to 12. And remember that x at t was equal to y at t, and that's 12 minus t. And then dx is equal to dt. And so really we'd have two of these 12 minus t, the quantity squared, times negative dt's. Cool so far? Awesome. So here we go. Our very first one, do you see zeros out? That's going to be 0. And then our second one, first part zeros out, but then we'll have 16 evaluated from t is 4 to t is 8. And that, I'm sorry, that would be 16t. And then that third one would be 2 times quantity 12 minus t cubed over 3, evaluated from t equals 8 to t equals 12. Good so far? Okay, so sorry, I lost my dividing line here. All right, so now that will be 16 times 8 minus 4, and then plus 2/3 times, let's see, 12 minus 12 would give us 0 cubed, and then 12 minus 8 is 4, so minus 4 cubed, which is 64, right? So we get 64 minus, let's see, 2 times 64 is 128 thirds, which would be equal to 192 minus 128 over 3, and that in turn would equal to 64 thirds, right? So there's a lot of stuff going on there, right? Which is why it's super cool that we just learned Green's theorem. I'm going to show you this, and I think you'll really like it. So this is the quote-unquote old way, okay, that we just did. And now this new way basically says, hey, if you meet all these requirements, right, then you just need to find the first partial of n with respect to x, subtract from that the first partial of m with respect to y, and do it over your region here, your region R. Okay, that simply connected region. So let's take a look here at what we would do for Green's theorem. All right, so using Green's theorem. So this was the old way, right? So old way. Green's theorem. So, here we go. Using Green's theorem, remember, we have our m. Let's identify what we have. Our m is y squared, right? And our n is the x squared. And we're working with, remember, this deal right here. And we're going to apply Green's theorem. And that's going to be the first partial of n with respect to x minus the first partial of y, or m, sorry, with respect to y, and then our area. So let's go ahead. Our first partial of m with respect to y is going to be 2y, and our first partial of n with respect to x is going to be 2x. Groovy? Okay, so our line integral here is going to be, so actually, we'll just kind of come up here because we have it written out up here. This is going to end up being equivalent to, so we're going to have the integral. It's a double integral, all right? And it's going to be in terms of dy dx, right? And so first off, let's do what was dn dx. It was 2x, right? And then we'll have minus 2y. Now, our area, so we're going to look at our, let's just copy our deal right here. And actually, you know what? We're not going to do that. We'll make another one because it's going to be, we're going to utilize it differently. Okay, so we have our x and our y. Okay. And remember, we had this triangle with vertices 0, 0, 4, 0, and 4, 4. And there we go. Okay, so what we have going on, remember, is if we're going to do a dy dx, then we got to have a function of x in that inner integral, right? And so here, isn't this the line y equals x? So as y is moving along, it's moving along from what to what? From y equals 0 to to the line y equals x, right? So we're going to have 0 to x, and that's what dy is moving along. Now, for our dx, what's going to happen is we're going to be moving along from what to what? Now you want it in terms of constants, right? So for our dx, it's going to be from 0 to 4. Cool? And let's do it. So we can take that 2 out, and we'll have the integral from 0 to 4, from 0 to x, of x minus y dy dx. Okay, so integrating, we'll have quantity x times y minus y squared over 2 And that's going from y is 0 to y is x. Cool so far? So then that will be 2 times the integral from 0 to 4 of, let's see, so we'll have our upper limit of integration will be x times x is x squared minus x squared over 2. And our lower limit of integration will zero out. Are you okay with that? Awesome. And then we'll still have our dx hanging out. So then that will be 2 times the integral from 0 to 4 of x squared over 2, right? 1x squared over 2 dx. So if I bring that 2 out, it divides out the other 2. So I'll just have the integral from 0 to 4 of x squared with respect to x, which will be 1/3 x cubed from x is 0 to x is 4, which is beautiful, 64/3. Cool, isn't it? So I don't know, which way you like better, but I think Green's theorem is pretty darn groovy. And note that this was a counterclockwise rotation that we had. And so our region, our simple region R, is always to the left of any object traveling along the path. So if you imagine you're in a car, and that's the view, or the region R is the view, the driver is going to always see the view most easily if you're in the U.S. All right. So anyway, that is Green's theorem. So here we go. Let's use Green's theorem to evaluate the integral. The line integral C of quantity y minus x dx plus 2x minus y dy for the given path. Okay, so this path here is it's going to be an ellipse, right? If you were to eliminate the parameter, what's going to happen? So you would have x over 2 is cosine theta, and y is still sine theta. But isn't cosine squared theta plus sine squared theta equal to 1? Good. So therefore, we would have x over 2 squared plus y over 1, if you want, squared would equal to 1. And that's because y was sine theta, which is y over 1. And x over 2 was cosine theta, right? So this is an ellipse with center, let's see, the bigger number is 2, and that's under the x. So with center HK, so actually the center will be, I'm thinking vertices, the center is going to be at 0, 0. And it's going to have a horizontal major axis. If you need to review your conics, you can go back to chapter 10.1, I think. And so let's see what it looks like. Let's see what the picture looks like here. So you would have something like this. Actually, I said 0, 0, right? And major axis is horizontal. 1, -1, 1, 2, 1, 2, -2, x and y. And so our shape will be at, if you let theta equal to 0, because we want to know where it starts, right? So you can look at the original. If at theta equal to 0, cosine of 0 is 1, so you'd have x equal to 2 and y equal to 0, so it's starting right here, okay? And then at theta equal to pi over 2, you'd have your x equal to 0 and your y equal to 1, right? So we can now tell our orientation is going to be, hang on, I'll draw it like this. So it'll look something like this. Cool, cool. So do you see that our region R, right? If you're driving along, you're going to be looking left all the time to see that view. Groovy? So we're all good. We can use Green's theorem. And so here we go. M is going to equal to what? Good. Y minus x. And so our first partial of M with respect to y is going to equal to 1. N is equal to 2x minus y. So our first partial of n with respect to x is going to equal to 2. Groovy? So this integral here, our integral along C of y minus x dx plus 2x minus y dy is going to equal to the double integral over the region R of our dn dx, our first partial of n with respect to x, minus first partial of m with respect to y. Well, that is just going to be, and then our dA here. Well, this part is just equal to 1, right? Because that's, well, we'll write it in. So that would equal to this region here of 2 minus 1 dA. Cool so far? Which is just 1 dA. But what is this? I mean, if you recall, this is an ellipse, right? So what is the area of that region? The area for an ellipse is equal to pi times a times b, which in our case is going to equal to, well, a is 2, b is 1, so we're going to get 2 pi, right? So the integral over R of 1 dA is just 2 pi. Isn't that cool? Because you're looking here, this part is equal to the area of the ellipse, which is 2 pi. Groovy? All right, so that is our result using Green's theorem. So example 3 looks a little more complicated. We're asked to use Green's theorem to evaluate this line integral here, which has a bunch of exponentials in there. And our curve is the boundary of the region that lies between the graphs of the circle x equal to 6 cosine theta and y equals 6 sine theta, and then the ellipse x equals 3 cosine theta, y equals 2 sine theta. Okay, so I just wanted to come here so you didn't think I was making stuff up. Notice that in region 3, if you're on that top line integral there, you're looking, you know, driving, looking to the left, right, going counterclockwise, then you see this region here, you would see this region here, right? All of this. But then on the second one, you'd have this other region here. You'd be looking to the left and you'd be in here. And so this one, it's not simply connected, but you can sometimes, if you have the right kind of situation, you can use Green's theorem and extend it to a region with a hole in it. So let's look at this third example and see how we can do that, okay? So basically, you've got this circle. So let's do a little work on this. You've got a circle that's going, x equal to 6 cosine theta. You would have x over 6 is cosine theta. And then similarly, y over 6 is sine theta. And remember, cosine squared theta plus sine squared theta is equal to 1. So we would have x over 6 squared plus y over 6 squared is equal to 1, which would give us x squared plus y squared is equal to 36, or 6 squared. Cool so far? Okay, so the x over 6 was cosine theta, and so that's how we got that one. And then we had y over 6 was sine theta. That's how we got that guy. And so then we have a circle with radius 6. And then we have an ellipse. X over 3 is cosine theta when you isolate cosine theta. And then y over 2 is sine theta. So then, similarly to the idea, cosine squared theta plus sine squared, I'll just write it out. Cosine squared theta plus sine squared theta is 1. So we would have x over 3 squared plus quantity y over 2 squared would equal to 1. So y over 2 is our sine theta. X over 3 was our cosine theta. And so what will happen is we're going to have, an ellipse with center 0, 0. A equal to 3, B equal to 2. That makes the major axis horizontal. And so now let's take a look at a picture of all this, right? So basically, okay, so our circle would be, let's figure out our orientation. So the circle here, if theta is 0, then we'll have the ordered pair 6, 0. If theta is pi over 2, then we'll have 0, 6. So we can see our orientation going like this. So this is our circle. I don't think my scale is very good. We won't use the tech, sorry. So our circle, I don't have the same scale for my X and my Y. So something like that. Sorry, it's not super great. And the orientation went like this. So as we're looking left, right, we have our region inside. Now let's look at our ellipse, right? So our ellipse here. The major axis is horizontal, again the center, 0, 0. And so A is 3, so 1, 2, 3, 1, 2, 3, 1, 2, 1, 2. So let's find our direction. So looking at the direction, here we go. If theta is 0, good, we'll be at this point here, 3, 0. Then it goes to 0, 2, negative 3, 0, and 0, negative 2. And so our orientation is going to go, Our orientation is going to go like this, which you might say, holy moly, there might be a problem, Houston, right? So here, I know what I said here, that this one is not simply connected up here, right? Right up here I said it's not simply connected. Region 3 itself is not simply connected. But you could look at region 3 as the difference of two different simply connected regions. So here, if you said, oh, if I said region 3 was equal to some region 5 minus some region 4, and the blue, this whole thing right here was region 5, and then this whole thing was my region 4, right? Then I could use Green's theorem. And so that's what we're going to do with this problem here, with example 3, I think it was, right? Okay, so basically, and the reason why it's going to be cool to use it is because we are going to take this pink region right here, and we know the area of it, right? Because we know the area for an ellipse. And we're going to subtract that from the area of this circle here. So we have this circle here, this whole circle. We can find the area of the circle. And so we are going to do that in order, basically use Green's theorem 2 separate times in order to find this. So let's check it out. All right. So again, we're going to look at this as 2 separate problems in the sense of we're working on one for the circle and we're working on one for the ellipse. Okay. So for the circle, M is equal to e to the negative x squared over 2 minus y dm, or the first partial of m with respect to y is equal to, that first one zeroes out, so we'll just get negative 1. N is going to equal to e to the negative y squared over 2 plus x, right? So the first partial of n with respect to x is going to be, beautiful, 1. So we're going to have line integral, right, is going to be, for this one, so this the line integral for e to the negative x squared over 2 minus y dx plus e to the negative y squared over 2 plus x dy is going to equal to the double integral over our region and then dn minus dy, right? So just write it all out. The first partial of n with respect to x minus the first partial of m with respect to y. And that is just going to be equal to 2, right? And that with our dA. And that is equal to 2. Sorry. We'll say 2 because we can factor that out. Now, what's the area of the circle? Pi r squared, right? So we're going to have 2 times pi times 6 squared. And that comes from this being the area of that circle. Okay? And that will end up being, what, 72 pi? Groovy? Okay, so the ellipse, on the other hand, you're going to have the same thing for dm dy or the first partial of m with respect to y and the first partial of n with respect to x. That's going to all be the same. So for our ellipse, you're going to, you're going to have this line integral okay, that's going to equal to our region R, and we're going to get, again, this, the first partial of n with respect to x minus the first partial of m with respect to y, and then dA. But that, my friends, is going to be equal to 1 minus negative 2, which is 2, right? And then this stuff here for the ellipse is going to be, remember it was pi times a times b? So pi times 3 times 2, which is going to be 12 pi. Good so far? So we used Green's theorem twice. Cool? Now what do we have to do? We have to subtract the results because we were looking for, at the end of the day, we wanted this region here, right? Right here. And so we need to subtract our results. And so at the end of the day, we will end up with (72 pi from the circle minus 12 pi from the ellipse, right? So at the end of the day, our result, the difference is, which is 60 pi. Cool, cool? All right. So that's the final answer, 60 pi. So remember, we did two different Green's theorems here in order to find that end result of 60 pi for the blue. That's our blue region. Okay, phew. All right, so now let's look at a theorem that goes over line integral for area. So if R is a plane region bounded by a piecewise smooth simple closed curve C, oriented counterclockwise, then the area of R is given by. Our area is equal to 1/2 times this line integral on C of x dy minus y dx. So use a line integral to find the area of the region R. So here we're looking to find the area of a triangle bounded by the graphs of x is 0, 3x minus 2y is 0, and x plus 2y is 8. So let's see. Let's see what these all are. So if I isolated y for this guy, I would have y is 3/2 x, right? And then if I isolated y for this one, I would have negative 1/2 x plus 4. So my highest y-intercept is 4. I don't have anything dipping below the x-axis, and I don't have anything that I need to worry about to the left. So 1, 2, 3, 4, and then let's see if this works, this scale. All right, so we've got our line. X is 0, so we're bound, from that by the x-axis, right? So we've got x is 0. And then we have y is 3/2 x, so 0, 0, slope, go up 3/2, right? Connecting the dots, got this line here. So this is y equals 3/2 times x. And then y is negative 1/2 x plus 4. So the y-intercept will be here. And then go down 1/2, so they'll intersect there. Cool. So now, here we go. In order to, we want it to be counterclockwise, right? So, so our little region is in here. And our orientation then, oops, that won't work. And so our orientation would end up going like this. In order for it to be counterclockwise, it has to go like this. Groovy? Okay, so there we go. There's our region R. We're good to go. Groovy. Let's do it. So going in order of our orientation, all right, our first curve was y is equal to 3/2 times x, right? So dy will be equal to 3/2 dx. Cool so far? And then we're going from zero is less than or equal to x is less than or equal to 2. So this might be a little reminiscent of, what we were doing when we were doing that one thing. We did it the old way, we did it the new way, remember? But we are not, the difference is we're not parameterizing. We're not getting a vector valued function. We're keeping it in terms of x and y. So notice that our interval is not along some parameter, and this is what's so magical and different about it. Okay, so that was our first curve. Our second curve, which we did in the pink, right? Curve 2 is y equals negative 1/2 x plus 4. And so dy is going to equal to negative 1/2 dx. Cool so far? And that, my friends, is going on the interval. Remember, we're going from x, where x is going. So x is traveling from 2 to 0, right? So it looks a little weird, but that's okay. 2 less than or equal to x, which is in turn less than or equal to 0. Our third curve, I'll do a darker green, is C3, which was x equals 0, right? So if x is equal to 0, dx is equal to 0. And so we don't have to worry about that one, right? So in general, this is what we have. We have our area is 1/2 along this line integral of x dy minus y dx. Cool so far? So what we're going to have is this. Our overall area will be, so we're looking at curve 1, all right, first. So we'll have 1/2, the integral from 0 to 2 of x dy. Remember, dy was 3/2 dx minus y. Well, y was 3/2 x, and then dx. So we have our y for this one was 3/2 x, right? And, oops, sorry, that was our wrong one. 3/2 x is our y for that one. And then our dy is 3/2 dx. And we got that from here. Cool, cool. And then now we'll go to that next line, or next curve. So in the pink, we have plus 1/2 times the integral from 2 to 0, right, of x dy. So dy was negative 1/2 dx for this one. And then minus y, which was negative 1/2 x plus 4 dx. So here is my y, and then here was my dy. Groovy? Okay, and then remember that last integral zeroed out because there's no change in x. So let's work on it. Our area will be equal to 1/2 times the integral from 0 to 2. What do we have here? Do you see we have 3/2 x dx minus 3/2 x dx, right? So we'll just get 0, right? For this one, or you could do 3/2 x. It would really be 3/2 x minus 3/2 x, that quantity dx is one way to look at it, which is just going to zero out. Then plus, we'll get 1/2 the integral from 2 to 0, and then we would end up with negative 1/2 x dx plus 1, actually, let's put them together. 1/2 x plus 1/2 x minus 4 all times dx, okay? Well, that's going to simplify to be 1/2 times this one totally zeroes out, right? And then these guys zero out, so we'll end up just having the integral of 1/2 from 2 to 0 of -4 dx. So if I factor out the -4, I would have -2 integral 2 to 0 dx. But remember, you can flip the order of integration if you change the sign. So we'd have 2 times the integral from 0 to 2 dx, which is just going to be 2 times x, from x is 0 to x is 2. So our area will just end up being 4 square units. Cool, cool? All right. So now there's some alternative forms of Green's theorem, depending on what information you have and what you're working with. So again, I'm not going to prove all these things. I just wanted to expose them to you. But it turns out that if F is a vector field in the plane, you can write that, basically a vector field in space if you write, F of x, y, and z equal to mi plus nj plus 0k. So finding the curl of F, we've done that before, right? Finding the curl of F right here. And, that's something we looked at earlier, right? Just a little bit earlier. So basically, if you've got the appropriate conditions on your vector field, your simple curve and your region R, you can write Green's theorem in the vector form. So it would be going along the curve of the vector field F dot dr, which ends up being that double integral over the region of the first partial of n with respect to x minus the first partial of m with respect to y dA, okay, which happens to also be equivalent to the integral over our region of the curl of F dot K dA. Okay, so that's the first alternative form. Now, assume the same conditions for F, C, and R. If you're using the arc length parameter S for C, you have R at S equals to X at S times I plus Y at S times J. So a unit tangent vector T to the curve C is given by R prime at S, which is equal to X prime at S times I plus Y prime at S times J. And that outward unit normal vector N can be written as N equals Y prime at S times I plus X prime at S times J. So for the vector field X and Y equal to Mi plus Nj, we have all right, so the line integral F dot dr, oops, sorry, not dr, dot N ds, right, because this one's going along the arc length, sorry. And that's going to be equal to the integral from A to B of Mi plus Nj dot Y prime at S times I plus X prime at S times J ds, and that in turn will equal to the line integral, oh, I messed this up, the integral from a to b of m dy ds minus n dx ds times ds. Well, that in turn will be equivalent to the line integral m dy minus n dx, which is equivalent, if you just swap them out, to negative n dx plus m dy, which is equivalent to the region dm, or the first partial of m with respect to x, plus the first partial of n with respect to y, dA, which is what? Beautiful. The integral of the divergence of f dA, which is pretty cool. All right, so here's all our alternative forms. I mean, at the end of the day, we were getting to this one here, right, and this one here. So that wraps it up for today. Next time we'll be looking at parametric surfaces. So I hope you have a wonderful morning, afternoon, or evening whenever you're watching this show. And if you like what I'm doing, hey, please subscribe and tell your friends. Bye.